Okay, so on this one, Benford's law states that the probability distribution of the first digits of many items, populations, expenses, etc., do not occur equally often. The distribution is not uniform, but has the probabilities shown in the below table, this table. Perform a hypothesis test, alpha 0.05, to see if these values are consistent with Benford's law. If there is strong evidence that the expenses do not fit with Benford's law, this means the expenses are not honest. They are fraud. So we've got the number of expenses with the leading digit. So basically there was a list of expenses. Like, so they took some company and they took all their expenses for the last year and they took the leading digits of those expenses. Maybe like the company says, I spent, $1,519 on a new computer for the office. And I spent $216 on a new printer. And I spent $47 on lunch one day and $930 on new office furniture. And then, they list out all the different things that the expenses that they did. And this is, then they just take the leading digits, 1, 2, 4, 9. Those are the leading, see it says leading digits. And they just keep a record. And so 46 of the times, their leading digit was a 1. And 18 of the times, leading digit was a 2. 19 of the times it was a 3. 14 of the times it was a 4. 3 times it was a 5. 9 times it was a 6. 5 times it was a 7. 7 times it was an 8. And 6 times it was a 9. Those were the, when they listed out all their expenses, that's how the leading digits went. Just the leading digit. We don't care about the rest of the numbers. We don't care at all. Just the leading digit. Now, why are we doing that? Well, because it turns out that this is a way they can test if a company is being dishonest or if some of the employees at the company are being dishonest, because it turns out that when we do things in life, tons of things, it's been proven. If you measure populations of different countries around the world, or expenses in a company, or digits in a digitized image, like a picture, you can digitize all the digital image. It turns out the leading digits will follow if they're honest, if they're not made up. Because if somebody was stealing money from the company, they could say, yeah, I spent $2,182 on office furniture, but really they just gave their friend or took themselves a check, wrote themselves a check for $2,182, right? It's not really, so if they're making up expenses that are false, we'll know it because if you take the leading digits and you compare them to Benford's law, that's what Benford's law states, you'll find that they don't match up. What do you mean, match up with what? Well, Benford's law has shown that really as we live life and do things, write checks and populations and all kinds of things, digitize images, I said, that they're going to follow these percentages really close. I mean, not perfect, but pretty darn close. Meaning the leading digit will be a 1 30% of the time. Most of it, like a lot of the time, will be a 1. 17.6% of the time, it'll be a 2. 12.5% of the time will be a 3, et cetera, all the way down to 9 will only happen 4.6%. 9 in front, like a number like 92 or 918 or whatever, will only happen 4.6% of the time. So what they can do, this is what they use. It's actually the IRS uses it to find out if we're being honest on our taxes. And all kinds of companies use it, accounting firms use it. It's actually law in the United States. Benford's law is that they can test things to see if they're being honest by Benford's law. And so that's what we're doing here. We're saying, okay, we've got all these expenses from this company, and they took all the checks they wrote, and 46 times the lead digit was 1, 18 times a 2, 19 times 3. How does that fit with what they should be according to Benford's law? That's what we're going to do. This is a goodness of fit test. How would we know that? If you look back here at the notes, you see goodness of fit, and it says for category percentages. That's what we have, category percentages. We're saying, see, there's a percentage for each category. That's a goodness of fit test. Benford's law, whoops, sorry about that. Benford's law is always goodness of fit. So we're going to do goodness of fit test. How well does the expenses reported by the company right here fit, goodness of fit with the percentages Benford's law says will always happen if things are being done honestly. Okay, so how are we going to do it? Well, go back to the notes. It says, we're down here for category percentage. What do you do? Each different value, each category percentage as a decimal multiplied. Oh, wait, sorry, up here. First up here, I should have said, copy and paste observed data values. So that's first. Oh, what calculator we go? We're going to go to the goodness of fit calculator. Yeah, I'm kind of skipping some stuff here. Good. I'm going to go to the goodness of fit calculator. And these right here, these are the observed. That's what we observed, right? 46 times the company had a leading digit of 1 on their expenses. And 18 times they had a leading digit 2, et cetera, et cetera. So that's what we observed. So we need to copy and paste. So this is the observed. We're going to copy and paste it. Let's go do that. So I'm going to go to the calculator. Let me go to the goodness of fit calculator here. It's number 20 down here on the bottom. There it is, number, sorry, 21. 21, goodness of fit, 21. So calculator 21, goodness of fit. And we have observed and expected. We're going to go to observe first. So let's go get the observed. We're just going to copy and paste the observed values in there. Come on down. Here's the problem. So I'm going to copy those observed expenses and paste them in there and just stick commas between them. You got to put commas, as you know, don't have to fix the spacing. So there's what they observed, you know, that's how many times for all the checks they wrote during the year, it's how many times the leading digit was 1, 2, 3 through 9. All right, now what did we expect? What are the numbers we expected if they're really honest checks? We expected they should fit with Benford's law. Well, how are we gonna calculate that? Well, that's a little more tricky. Let me help you with that. So what you have to do for that is you have to take, well, let me show you in the notes here. It says for the expected, you're going to take each category percentage as a decimal times the total of all values. That's how you can do the category percentages, what's expected. Then list these values like boom, boom, boom with commas. Okay, that's what we have to do. So I'm going to take, first off, I need the total. Total equals. So you're going to have to add all those up. First off, we're going to have to add all those numbers. So you can just do that in your calculator. Here, I'll go do it. I'll show you. Go to the calculator. I'll go to the scientific calculator down here, but you can do it on whatever calculator you want. I'm going to add those numbers up. 46 plus. You can just go back and forth and look at the numbers. I just wrote them down. There we go, 127. 127. So I just added those up. The total is 127. So 127 different checks were written during the year. 46 of them had a leading digit of 1. 18 of them had a leading digit of 2, et cetera, et cetera. So total is 127. Now, what do? For these is you take each category percent, like I'm going to take that first one, and I'll make it a decimal, so 0.301, take this one right here, 0.301 times 127. And then hit the buttons on the calculator, you'll get 38.227 if you multiply that on the calculator. And then the next one, take 0.177, change each, every time, notice what I'm doing, I'm moving the decimal like 1, 2, 1, 2. You always move the decimal 2 places back. I think a lot of people get confused because they look at, wait a minute, sir, but it's 3 back. Well, yeah, because it started out 1 back. So if you move it 2 more, it'll be 3 back. So don't think about what it ends up. Just think I need to move it 2 more from wherever it was whenever I change from a percentage to a decimal. So and then each time you're going to multiply by 127 on a calculator. And whoops, I already did this and I'll just give you the results. I'm doing it on my calculator. And so 0.125, again, decimal goes back 1, 2 times 127. And that comes out 15.87. It's a little tedious. That was that one. Next one. Now this, watch out, this one, 2 places back. So 1, 2, that's going to be 0.097, isn't it? See how I went back 2 places there? The first jump, you know, it started off right here, then it went 1, 2, didn't it? See that? Multiply that in your calculator, you're going to get 12.319. Okay, the next one. Again, 2 places back, 0.079, because again, it started out right here, 1, 2. You're always going 2 places back. And that comes out 10.033. And then 6.7. So 0.067. Again, start out here, 1, 2 places back. So 127 is 8.509. Just go to a calculator. And then 5.8 is the next one. It's 0.058, because start out here, 1, 2 times 127 is 7.366. We're getting close. Next one, 5.1, 0.051. Again, start here, 2 places. Times 127 is 6.477. And then the last one, 4.6, 2 places back, 0.046, right? Because right here, 1, 2 times 127 is 5.842. Okay, so all of these, because these are the expected. That's what we expected, because if Benford's law, if this company is honestly writing checks, then they should follow Benford's law, meaning they wrote 127 checks, and Benford's law tells us 30.1% of the time they should have a leading digit of 1. So in other words, 0.301, 30.1% of the 127 checks should, which is 38.227 checks, should have had a leading digit of 1. That's what we're doing. And 17.6% of the 127 checks should have had a leading digit of 2. That would be 22 checks, 22.352 of the checks should have had a leading digit of 2 if they're really honestly following Benford's law. And if they're doing honest, I don't mean they're trying to follow Benford's law, but Benford's law says that's what will happen if you're just honest in your interactions. It'll follow Benford's law. So if they're really being honest in their interactions, they, you know, for the 127 checks they wrote during the year for expenses, 38 of them should have had a leading digit of 1, 22 of them should have had a leading digit of 2, 15 of them should have had a leading digit of 3, et cetera, et cetera. That's following the Benford's law percentages of the 127 checks each time. So we're going to put all these numbers now into the expected in the calculator. Let's go and put commas between them. So we go back to the calculator, come up here, or up to the expected, I mean. We're going to put in those numbers. So this is a little tedious, 38.227, comma, that's the first one, 22.352, try to be careful, comma, 15.875, comma, 12.319, comma, 10.033, comma, 8.509, comma, 7.366, comma, 6.477, comma, 5.842. All right, got them all in there. Hit calculate. There's our x squared called chi-squared and our p-value 3392. See if that's right. Yep. So we got, there's the chi-squared called the test statistic. That's the x squared is chi-squared really. There's the p-value. Let's draw a conclusion to this crazy thing now. Remember how this works? Oh, maybe I probably should have shown you the HO and the H1. Let's do that. Let's come up here. And let's put it in. What's the HO? What's the H1? They didn't have us do it, but goodness of fit test. Goodness of fit test. So how do we actually do the conclusion here? The HO is observed and expected data fit well. So HO is they fit well. And H1 is the do not fit well. Do not fit well. Do not fit well. I'm just getting that right off the notes, right? See right here on the notes, goodness of fit test from the Unit 4 notes, okay? So, so what was our conclusion? Well, here's our p-value, okay? So our p-value is 0.33. Was that higher or lower? So p-value 0.339, so I'll put the p-value right here. P-value 0.339, the alpha level. What would p-value 0.3392, 1, 2, whatever. The alpha level on this problem is somewhere which I cannot see right now. Oh, there it is, alpha 0.05. All right, so our p-value is clearly greater. All right, you know the saying, right? If the p is low, then the HO, the null, must go, meaning go away. Was our p-value low? No, our p-value was not low. Our p-value was greater. So if p-value is not low, the HO must not go away. So we're going to fail to reject, right? We're not going to reject the HO. The HO is not going to go away. We're going to fail to reject HO, which means what? We're keeping HO. We're not rejecting HO. We're keeping HO. All right, so and so coming on down here, the p-value is greater than the alpha level. So what's our decision if we're keeping HO? Let's go back. What does HO say? Fit well. Fit well. What does that mean? Fit well, fit well. Meaning we're saying there's a pretty good fit between what the company reported their leading digits of 1, 2, 3, 4 with what Benford's law said should happen. There's a pretty good fit. So if they fit well, then the company is honest. If they didn't fit well, that would mean dishonest. The company's lying. They should fit with Benford's law. So we conclude they fit well. The company's being honest. There's no fraud here. So our conclusion. Oh yeah, and the evidence. I forgot to tell you about the evidence. Yeah, here's fail to reject the null, as we said. Fail to reject the null. Right? Fail to reject the null. And remember, HO is always weak evidence every time, and H1 is always strong evidence every time. We kept HO. So that means we're going to believe exactly what HO says, which means there's weak evidence. They do seem to fit well. We think the company's honest. So there's weak evidence. So our conclusion is that there is not reason to believe the business expenses are the result of fraud. Fraud means lying. We believe there's not evidence that they're lying. And so again, that conclusion was tricky. It was all about HOH1. Now, they never made us write HOH1, but I went ahead and did it anyway, and that really helped. So make sure you do that. Where did I get HOH1? Right from the notes. The Unit 4 notes, HO says observed and expected fit well. H1 says observed and expected do not fit well. That's for goodness of fit test. So I put that in. Fit well, do not fit well, HO, And we know HO is always weak evidence. H1 is always strong. Then when we came down here and we found that our p-value was greater, if the p is not low, the null must not go. So we failed to reject the null. We kept the null, which means we're going back up and keeping exactly what the null says. Weak evidence, they fit well. The company's being honest. Honest because their data fits well with Benford's law prediction on what honest behavior would look like. And so there's our conclusion, and there we go.